It doesn't matter. Good morning again, and this is where we start the recording right now. Anyway, so I sent him a PDF file, and I'm sorry about that. I thought I did it two ways. I sent the link on Canvas so that you should be able to open it if you completed the tasks, and that was in the body of the message, but I also included it as a separate attachment, and apparently Canvas picked up the fact that these are the same file name, although it was coming from a different repository, so it should not really have been restricted, but for some reason it was. So anyway, I'm going to go through that file today. We're going to go through the steps, is because the calculations are kind of lengthy and sometimes they're time consuming. So I wanted you guys to have that file. It's a 4-page file, and it's in-depth basically analysis to the statistics basically of part of this chapter. So that's basically what the whole idea is. So if you were not able to open it because of the fact that you did not complete week 1, because week 2 relies on the fact that you have to complete all the tasks for week 1 and submit what you need to submit and all of that, then it's fine. You can look at it later on and you can browse through it. We have quite a few people who are missing today for some reason, and we have a lot of work to work on. We have, in addition to the fact that we have to finish the chapter 18, we also have a few examples that I would want to go through from toward the end of the book. Those are problems from the chapter problems, really. So we have to go through those. In addition to the fact that we have a lab, brand new lab, that I want to go through it. And there is a catch-you, basically. There is an issue, not really an issue. I noticed it in the past where students do not pay attention to a small detail in the attached Excel file, and they end up with nonsense errors. They end up with huge errors. So I want to make sure that you guys don't fall into that trap, really, okay? So those are the things that we need to cover today. So let me first of all pick up the file to where we left. So let me pick up the PDF file. If you were able to open it, please open it now. If not, you can follow with me in here. And it's really my notes, okay? This is my notes on it. And I'm going to show you the file both in PDF form, the one that you should have received. And I'm actually going to dive in at some point into the LaTeX version of it to show you how the graphs were generated, to reiterate the fact that those graphs are actually accurate depictions of the actual distribution of these velocities for these molecules. Again, we are sometime, let me share the screen. So this is the PDF file that you should have received. Okay, it's the kinetic theory of gases using the Gaussian distribution. There is basically one integral that keeps on repeating itself time and time again in all of these 4 pages. Okay, in all of these 4 pages, it's the same integral time and again. As a matter of fact, I'm going to open today Mathematica, and I'm going to define that function and start working off of it, because we're going to do it time and time and again. So the point being in here is we found the RMS speed. Let me stop sharing quickly here to show you where we stand in terms of our notes from last week. Share now the OneNote. So last Tuesday, 2 days ago, we were able to find this RMS speed. Square root of 3 times Boltzmann constant K times the temperature of the gas divided by the mass of each and every one of those molecules. Okay, so if we're talking about oxygen, that's 32 grams per mole. But that's a mole, that's an Avogadro number. So I have to still divide it by 6.022 times 10 to the power 23 to find that little m. Okay, to find the mass of the oxygen molecule, which is O2. Okay, you have 16 grams per atom of oxygen, but you have 2 of them. So you have a total of 32. If it's nitrogen, we're talking 28 grams per mole. If it's hydrogen, we're talking roughly about 2 grams per mole. So this is the mass that determines that, meaning that the lighter the molecule, like hydrogen, hydrogen gas, the faster it's going to move, because you have it in the square root in here in the denominator. Okay, you have it in the denominator. That's why those lighter molecules will be moving faster than the heavier ones, the temperature being the same. So this is what we believe happened to Venus, actually, because at some point it had water on its surface, but a few 100 million years ago, about 150 million years ago or so, the planet went through a extreme heating process, either through maybe an impact from a meteor, and plus a lot of volcanic activity that evaporated all of that water, basically H2O. The molecules of the water and the molecule of the oxygen separated because of the extreme heat. Then you have the oxygen that recombined with the carbon to form carbon dioxide. But because the hydrogen is a lot lighter, it escaped the atmosphere of the planet, and now the planet is devoured, does not have any water anymore because of this process. Again, because of this fact. And the Earth also is losing a lot of its hydrogen because of the same reason, but Earth is replenishing it on a regular basis because of the outgassing processes. So the Earth is maintaining a little bit its atmosphere because of this volcanic activities and other processes that basically replenish the atmosphere. So this is a fact that the square root 3 kb over mt over m, this came about of making this model, basically of making these assumptions that we made last week for the ideal gas and how it looks like. You guys remember I made several assumptions about it, about the fact that it meets the statistics requirement, and also it's symmetry in all directions, isotropic, the mass is over volume is so small, and collisions being elastic, and the particles are so tiny. So at that point, we really have no idea that the atomic model even existed. We're talking about the late 1800s, and at that time, the model of the atom did not even we knew about the electrons, they exist. So we made the assumption that because matter is neutral, so there must be positive charges to counterpart this negative charges, and that's what probably the smallest building blocks of matter are. But this thermodynamics business, a lot of people argued against the fact that there is atoms involved at all. This is based on energy, okay, transferred between different media, and that's what the temperature is. But this model somehow gave us an explanation of what the temperature is. The temperature apparently has to do with the average kinetic energy of those molecules. Okay, this is really what this whole thing came about. That expression, this expression is coming from this one. Okay, so this temperature has to do with that. So again, this is where the model led us to. This is also, there was a big criticism for that model, in fact, that the speeds were so high. We calculated the speed for nitrogen, we found it to be far more than the speed of sound. So this, you're telling me that these things are zooming in and out with a faster, supersonic, basically, particles going every which way. How come we don't see them? How come we don't feel them, other than what you're calling a temperature? Well, in here, the mean free path and the mean free time will make sure that that does not become measurable, in the sense that they don't travel that far before they collide. So we don't see them in this on a macroscopic level, those motions, supersonic motions, because of this fact. So again, this is where we stood from last chapter, from this chapter actually, and we are now making the following assumption, because we know that that's an RMS value, that's a root mean square. So it's some sort of an average. So there was a distribution that was that we had to make, and that is actually Maxwell made that assumption that this, actually it's not an assumption, I mean it's based on statistical arguments, sound statistical arguments that are beyond the scope of this book, that any molecule moving in a speed between v and v plus dv, it's given by the probability of some distribution function f of v dv. Okay, so this is a probability. I mean, at best, it's going to be 100%. At worst, it's going to be 0%. So this number is between 0 and 1. Okay? If we know for sure that it's moving with a speed that is between this range, then this number should be exactly 1. If it's moving, if we're not sure, this probability will tell us how sure we are. So this is basically what this number means, okay? Now, if you're asking me how many particles are actually moving with that speed, all I have to do is, if I know their total, all I have to do is tell you n times this number, and that somehow gives me the n, okay? So this is the number of particles that are moving in the range between v and v plus dv. So this is basically an introduction to the statistics. This is not the full picture. I mean, the arguments for it are really, really, it's one of the most complicated sciences, because you take F equals to ma. This is, by the way, where we started from in this chapter, when we said the impulse and the momentum, and they're actually rooted in F equals to ma. You make those assumptions, and then you take the ensemble of all of these particles, and now you have a collective behavior that is determined by the statistics. Okay, so this is basically as far as we're going to introduce it. The point is, we needed to find a closed form for the function f, and for that, he used the Gaussian distribution. Now, normally the Gaussian distribution is just the exponential function of some number in here, of some x squared in here. Okay. But because we're integrating over all of the velocities, normally this integration is the dvx, dvy, and dvz. And when we convert this to polar coordinates, a v squared will appear, and then dv plus the angular distribution, the azimuthal angular distribution, and also the other one, the what do you call it? The azimuth and the declination. In astronomy, they call it declination. I forgot the name for it right now. And it's the theta angle and the phi angle, okay? But those two numbers, they're symmetrical. We're assuming isotropic distribution, so they're just going to pick up some normalization factors. And now you have the v squared, so that's why you have the x squared in front of it, okay? Because you are pulling the magnitude of the velocity, dv. Okay, so this integration becomes over x. So this is how the function would look like, barring a constant c. So this is how f of v would look like then. F of v is some constant, which I'm going to determine quickly, and we'll have the reasons why we determined. This v squared is coming from the fact that we're considering all of the volume of the velocities between v and v plus dv, because this is technically a magnitude. So if you look at it in space, so the v can have a vx component, a vy component, and a vz component, and can be anywhere on this space. So this is what we mean by the v and v plus dv. So it's a cube actually in here. And that is really the volume that we're considering in here. Granted, all directions are symmetrical. That's why we're pulling just the magnitude in here. And that's why the v squared comes in here, okay? So I think enough explanations. I explained a lot about the roots of it. The book does not even go to these details. And in here, I have the ratio of two energies. I have the ratio of mass times velocity squared over 2. That is the kinetic energy, if you guys remember. And kBt, which is coming from the fact that this is also an energy, but I'm scaling the kinetic energy over this factor, okay? So both of them are energies. This is joules over joule. And this is the function that we want to find, okay? This is the function that we're going to be working with. The exponential, by the way, has to have a cosine and sine functions. They all have to have an argument that is unitless. That's a number, okay? That's why you have a joule over joule. As a matter of fact, v squared over 2 kBt over m, that is actually a velocity squared over a velocity squared. What I did was move the m downstairs in here. So this number is some velocity squared over some nominal velocity. which is, we call it V naught in here, is just the square root of 2 kBt over m. This is just to make this unit in here, this exponential in here without units. Because if I write it V squared over V naught squared, this is a dimensionless number. This has no units now. Meter squared over second squared over meter squared over second squared cancel out. And at the end, I will have no units. So expressed in this dimensionless unit x, then the whole math comes out. So let me stop sharing this screen in here and share with you the PDF file that I sent you. Share the PDF file. Okay. So this is the whole argument in here, that this distribution is given by some constant, and we're going to talk about that constant, times v squared times exponential of negative m squared over 2 kBt. Remember, mv squared over 2, that is the kinetic energy, and kBt is the unit due to the thermal agitation, okay? That is coming from statistics actually in here. C is a constant. How can we determine C? Here is the argument of how to find C. It's called the normalization factor because usually the probability of an event depends on how many events you have. For example, between a coin, you have a heads and tail. You have two cases in here, either heads or tail. What is the probability of getting a head? If I flip the coin, it's one event, which is head, over all of the probabilities in this case. So it's going to be 50%, okay? So instead of dividing by 2, I'm going to normalize that and make it 1. That is basically what this means. That means that there is a probability 100% for sure that I'm going to either get a head or tail. I mean, if I flip this coin, there is 100% sure, accurate prediction that I'm going to either get a head or tail. That's what that means, okay? So in here, the molecules for sure will have a velocity between 0 and infinity. No matter what, any molecule from all of the huge number of molecules will have for sure a velocity between 0 and infinity. In magnitude, that's what we're talking about in here. That's where the v squared came in. So that's how we can determine C, by requiring that the sum of all of the probabilities be 1 from 0 to infinity. So from here, it's just a matter of finding this integral from 0 to infinity of v squared exponential of all of that stuff dv. So again, I'm reintroducing that v naught in here, which is a scaling, scaling factor for the velocities in this case, because it comes in natural in here in this exponent. I have negative v squared over 2 kBt over m. So better 2 kBt over m become a velocity, because kBt is in joules, which is in Newton times meter, and in Newton is a kilogram meter per second squared. So it's a kilogram times meter squared per second squared divided by kilogram. Cancel the kilogram and the kilogram, and you end up with square root of meter squared per second squared, which is a meter per second. So this is a good, honest velocity. 2 has no bearing on the units. It's just to make this thing by itself x squared, that's all. Okay, so at this point, it's an innocent velocity. It has no meaning whatsoever, other than the fact that we're scaling this expression. Okay, so we're going to make the variable change then, that v is v naught x, where x is a dimensionless number, as I was saying, and dv becomes v naught dx. And if we carry all of these calculations, this is just v over v naught squared, which is x squared. So the exponent is done for. The only problem is you have this v squared now. And v squared becomes v naught squared x squared. So the function f of v that we started with becomes a function of x, where the scaling factor now is c times v naught squared, and everything else is dimensionless now. Don't forget, in the integral, you have another dv. And that is going to put another v naught also times dx. So at the end, you have a c v naught squared cubed, the integral from 0 to infinity. Up to this point, everything looks fine. This is a number now, because this is a bounded integral between 0 and infinity of this dummy variable x in here. So whatever you end up with in here, it's going to be a number. Whatever that number is, we don't care. It's going to be a number. times c times v naught cubed must be 1. From here, we can find what c is. That scaling factor for that one in here. So we're going to do this by parts. We're going to say x exponential of negative x squared dx. That's nothing but the derivative of exponential, or d's differentiation of the difference, if you want to call it that way, of negative exponential of negative x squared over 2. Because if you take the derivative of this expression, you will have negative times negative, that's positive, 2 divided by 2, that cancels, and then you will have an x in here times the exponential, and that is one of this x squared. But you have left with another x in here. So when you do the integration by part, you multiply this function by this this integrand, and you take the limits between 0 and infinity, because those are the boundaries of integration. Now minus this number times the d sub x. Here is a d sub x, but you have a minus in here. So there is a minus times minus becomes a plus, and you have a factor of 1/2 that comes out, and you have the integral now of just this exponential by itself. This number is 0. The reason why it's 0 is because in the lower limit, it's 0 times exponential of negative 0, which is exponential of 0, which is 1. So you have 0 times 1 divided by 2, which is 0. In the upper limit, it's dominated by the exponential. The exponential goes to 0 faster than the power law as it blows up. So in this case, this expression also goes to 0. So you have 0 minus 0, which is 0, plus this integral in here. Don't forget the c times v naught cubed in here, times the factor of 1/2. Now here is this function under the integral is an even function. Because it's an even function, one of the fundamental properties of the integral, it's 1/2 of the integral from negative infinity to positive infinity. So there is another 1/2 times 1/2. So we have a factor of 1/4 now, 1/4. Okay. Because the 1/2 is coming from this property of the integral, and the other half came out from this partial integration by parts. So you have a factor of 1/4, and you have the exponent, the integral of negative infinity to positive infinity. This is the Gaussian integral. Okay. For that, there are all kinds of methods now of how to do the Gaussian integral. Okay, let me stop sharing and share with you my notes again. Because remember, we have cv naught cubed over 4 times the Gaussian integral. So let me share this Gaussian integral now. So this is what we ended up with. We ended up with trying to find what this integral between negative infinity and positive infinity of exponential of negative x squared dx. Okay? This is what we need to find. For that, I'm going to consider the following integral. I'm going to find the integral from negative infinity to positive infinity of negative x squared dx, and negative infinity to positive infinity of negative y squared dy. This is on the plane. This is on the plane when I'm having x-axis is this way, going from negative infinity to positive infinity, and the y-axis going from negative infinity to positive infinity, and doing the integral on either axis, on both axes actually, separately. Going from negative infinity to positive, obviously I'm going to describe the whole plane if I do that. dx changes independently, and dy changes independently, so that the element of surface in here is dx times dy. And that element of surface, dx dy, sweep the entire plane, sweeps the entire plane. From negative infinity to positive infinity, whichever way you go. Either you go through the whole y-axis, x-axis, and take your way up through the y-axis, or you go through the entire y-axis and come along in here. It doesn't matter. Those are independent variables. As a matter of fact, this is the integral I itself, and this is the integral I itself. So this is nothing but I squared. Then this is one way of finding I squared. We're going to make a change of variable. So I squared really is nothing but the integral from negative infinity to positive infinity for both axes of dx dy of exponential of negative x squared plus y squared. This is coming from the properties of the exponential no more. Okay, we're going to make the following change of variable. We're going to make x equals to r cosine theta and y equals to r sine theta. These are polar coordinates. So instead of sweeping the plane the way we described it initially, it's the same plane, by the way, we're going to use polar coordinates with a coordinate r hat in the r hat direction, whose angular displacement is theta. I can do this, varying this vector dr by doing one of two things, either changing its length by an amount dr in the r hat direction, or changing its direction by an amount d theta. So this is the amount d theta. So that this is equal to r d theta. The arc tended in this direction is r d theta. Obviously, d theta is very, very small. That's why I'm making it a small line. It's supposed to be an arc, but because d theta is so small, the arc becomes a line. Okay, but it's going to be perpendicular to this vector. So this is the displacement. So dr as a vector is going to be dr in the r hat direction plus r d theta in the theta hat direction. Okay, so this is the element of surface now that I'm taking. The element of surface is clearly the length is dr and the width is r d theta. Okay, so this is the element of surface, except r changes from 0, no radius, all the way to infinity. And theta goes from 0 to 2 pi, and that's it. That's all I need, because I don't need to have theta vary more, because I want to sweep the same plane I did before, except now using the polar coordinates. So theta can vary from 0 to 2 pi. Okay? The element of surface is clearly r dr d theta. So if I do that change of variable, now I have another way of finding the same square of that integral, which is the integration over r from 0 to infinity, the integration from theta for theta from 0 to 2 pi of r dr d theta times exponential of that negative x squared plus y squared. From this expression, it's clearly x squared plus y squared is equal to r squared times cos squared plus sin squared. And this is 1, no matter what. So this is r squared. The exponent of the function becomes just exponential of negative r squared. D theta is independent of r, and d theta there is no occurrence whatsoever in this expression under the integral. So that's all it's going to give me then is from 0 to 2 pi, it's going to just give me 2 pi. And I'm left with 2 pi, the integral from 0 to infinity exponential negative r squared times r, this r, times dr. And now this is a simple integral. I can do this because exponential of negative r squared is nothing but the negative, it's antiderivative of negative r squared over 2, evaluated between 0 and infinity. Because if I take the derivative, I will drop negative, which cancels that negative, and I will drop 2, that cancels that 2, and I will drop another r in here, that's 2r, and that is that r exponential of negative r squared. Times, of course, the 2 pi, don't forget the 2 pi in here. The whole thing is multiplying 2 pi, which cancels one of these 2, cancels that 2, okay? And then you'll be left with a pi times exponential of negative infinity, that is 0, minus times minus, that's plus exponential of negative 0, and that is 1. So the whole thing is just pi. So that is why I squared is equal to pi, which means that the actual integral itself is just square root of pi. This is one way, and this is the easiest way, honestly. Not necessarily the easiest way, but this is one of the easiest ways of finding this Gaussian integral, okay? Does this make sense to you guys? Matt, if you said something, I did not hear it. Make
Trying to
sense?
follow him, right? I was writing it all down.
Okay.
It makes sense.
Okay, very good. So here is the deal. Okay, I put it for as notes in here that you should receive. Again, I put the same double integral in here. There is a different method that is popular also, and there are all kinds of methods. Once somebody finds a solution to a problem, a million other people will find different ways. Okay, there are at least 6, 7 other methods to finding the same result. The point being in here, one of them is actually what is it? Feynman way of integration, converting this into a parametric integral, and then basically taking derivatives and try to find the simpler form for it, and at the end you're going to get the same result. Okay. Another way of doing it using a function z equal to exponential negative x squared y squared, and then finding the volume under that. It's basically to that dimensional surface, which is similar to this one, and cutting the volume in different ways, this way or that way, and then changing it and taking note of how that. So all of them will give you the same result, which is square root of pi, and that is the main thing in here, that this integral is square root of pi. Okay, so again, this is just a repetition of what I just shown you guys. So this is an integral in the xy plane, making the variable change the r cosine theta and r sine theta. The element of surface, by the way, I made a correction to this one. So if you guys, because I forgot to make a space between the obviously and this variable in the dx dy is actually an element of surface. And when you take vector calculus, you will know how to find the surface, which is a cross product of the one side times the other side, whereas the volume is the mixed product of the dot product and the cross product to find the volume, which is a number, whereas this one is actually a vector. Okay, it's going to be pointing in the z direction. Anyway, it's going to be r d theta, and the simple argument that I made by using geometries should work good enough for you guys. And the integration between 0 to infinity theta 2, that's going to sweep the same space in here, the same plane. And once you do that, then the integration over theta becomes just 2 pi. And then the integration over r dr exponential, that is nothing but this exponential in here, evaluated between 0 and infinity, and at the end you get pi. So I itself is equal to square root of pi. So let's go back into this expression here, then equation 1. So this is square root of pi, not pi, square root of pi, times c times over 4 times v naught cubed. From here, we can find what c is. That's the whole purpose of this, to find that normalization factor. Once you find c is, this is how c looks like. It's 4 over square root of pi times 1 over v naught cubed. And just subbing the value of v naught in here, you can find this value. The book basically gives you the value in here without showing you where it's coming from, and it leaves it as a homework where you're going to find a homework problem where you're going to find what c is. So the homework problem is already done for you guys using this method in here. So the function now f of v, you sub the value of c that we just found, and looks like this one. In terms of v naught, the scaling factor that I was talking about for the velocities, c is just 4 over square root of pi times 1 over v naught cubed times v squared. And if we redefine again that x being just the ratio of the two velocities, so you have v squared over v naught squared in here, so you'll be left with a v naught in the denominator, and everything else becomes a dimensionless number. So if I put v naught equals to 1, or I scale it according to v naught, this function I can plot. Okay, and this is an accurate depiction of this function. So let me share with you where I got that function in here, just to show you that this function is accurate to the point that you're going to see it. Are you guys familiar with LaTeX? Any one of you guys worked with it at all?
No.
Okay, it's actually a good software to write scientific, basically mathematical equations in general. And you can draw diagrams, you can draw circuits, you can draw all kinds of things. One of the things that's useful for it, and I love it for it, is plotting functions. Okay, so this is the function in here that I'm plotting using this text picture package. And you can go through basically the steps. But the point I'm trying to show you in here is that this is the same function I was talking to you about. This is the same function that we have it in here. This is 4 over square root of pi, which is 2.25676 times x to the power 2 times the exponential to the negative x squared. This is the function we're trying to plot in here in units of v naught, because v naught in here, I'm basically multiplying everything by v naught in here to make it dimensionless. Okay. So that's the whole thing. That's why you see 1 in here. And that's why you see the maximum in here is where this point, the red point in here. Okay. So, and this plot in here, the function itself goes to 0 on both sides. When for the small velocities, obviously when v is equal to 0, f of v is equal to 0. Doesn't matter what the exponential is. When v goes to infinity, the exponential dominates and it also drops to 0. So there is a maximum of some sort in here, and that is this point. And this is a distribution of the velocities as a function of v naught. Okay, of course, the VRMS in here is somewhere in here. We're going to talk about this one in here. The 3 points that you see in here in red, I actually included a file data in here, and that file data is red and added to a new plot, and they are marked in here in this graph. The reason why I'm showing you this is that this is an accurate depiction of this function. Obviously, the range is from 0 to 3 only. 3 in this units of v naught, 3 v naught, if you wish. Okay. Particle can move with a lot faster velocities, but practically they will have zero of them that do move at that speed, or those speeds. Okay. So this is basically what this function is. So let's continue with the PDF file. It's the same thing. It's this one and that one have the same thing. Actually, let me move this. I use it for making exams, by the way, and things like that. So this is a midterm for another class. So it's a very, very useful software. So anyway, so that is, we need to find the most probable velocity. For that, all we have to do is take this function and take its derivative and make it equal to 0. That's how we find the maximum of any function, or the minimum for that matter. So if we take the derivative of this function with respect to v, it's as if we're taking the derivative with respect to x and multiplying by the derivative of x with respect to v, and that is just 1 over v naught. So if df over dv is equal to 0, that means df over dx is equal to 0. So it's good to work with this dimensionless number x and take the derivations. So the derivative of x squared is 2x times the exponential minus x squared times the derivative of the exponential, which is 2x times the exponential itself. So you have a 2x that comes out as a common factor, and they have the exponential that comes out of a factor, and you'll be left with 1 in here minus x squared. There are 3 points where this thing can vanish, either at x equals to 0, and this makes this 0, or x going to infinity, and that will make also this one is 0, or x is equal to 1, and that also will make this one 0. The 2x equal to 0 and x equal to infinity, from the graph you can clearly see that those are meaningless numbers. There are practically hardly any more. This is 0 particles moving with the velocity 0, and this is very unlikely also scenario because there is hardly any particle moving with a velocity that is infinite. So the only value in here for the most probable velocity is 1, x equals to 1, which means v equal to v naught. So that v naught that did not have any meaning to begin with now has a meaning. This is the most probable velocity. So the square root of 2 kbt over m is the most likely velocity that you're going to find your particle in. That's what x equals to 1 mean, that v is equal to v naught. So this is, if you take any molecule out of the bunch that you have in the air right now, the most likely velocity that you're going to be finding is square root of 2 kbt over m. Remember, the RMS is square root of 3 over kbt over m. This is square root of 2 kbt over m. So this is the most likely velocity you're going to find. The average speed. Now, how much average you're going to find? You're going to do the same thing. You're going to do now the v average. You average this quantity over this distribution. On average, this is the value. Remember, this is the distribution. This is how much each molecule is most likely going to go from v to v plus dv, but you want to find the average, so you multiply that by the probability, v times the probability, and you add up from 0 to infinity. That is how the average is going to be found all the time. The reason why I didn't divide by all of the probabilities in here, because that is 1. That is coming from the normalization C. If we didn't do that step, we would have to divide by that number. What is the probability of finding velocity from 0 to infinity? That is 100%. We know that there is a molecule that is going to be moving with that speed. If we do this integration now, and you move everything in here, you're going to find, because remember, f of v dv this is f of v. You have v over v naught, v squared over v naught squared, v naught cubed. So you'll be left with a v naught in the denominator. But there is a dv in here that is going to pull another v naught. That's going to cancel that v naught. But there is another v that is going to appear, and that is coming from this v itself. So if you do the substitution carefully, you're going to find that 4 v naught over square root of pi, because the v naught cubed in the denominator get canceled by the v that just appeared and the v squared. Those are v cubed already, and the dv. So that's v naught to the power 4 divided by v naught cubed. So at the end of the day, you will end up with a v naught in here. And everything else now is a dimensionless number. Now this integral is easy to do actually. Once you have an odd number of powers in here, this is actually easy to do with parts by parts. You do it as many parts as possible to get to the final answer. So the first one is noting that x exponential of negative x squared dx is just the d of that negative exponential of negative x squared over 2. You have seen this already, okay? And using the integration by parts. So one of this x cubed is going to be consumed in here. So you'll be left with an x squared. So negative x squared over 2 times the exponent. And that too goes to 0 on both ends, at positive infinity and negative infinity. At 0, it cancels because of this 0 squared. And at infinity, it cancels because of the exponential dominating the power. So both of them is 0. And you'll be left with this exponential of negative x squared over 2 times d of x squared, because remember you have an x squared in here, and d of x squared is 2x exponential of negative x squared. So the 2 in here does not cancel this 2 but cancel this 4. So leave this 2 alone in here. Don't mess with it. Okay, so I left it by itself in here, and I canceled that 4 with that 2. But the 2 in here, x exponential of negative x squared, just is just the differential of that is the entire, its entire derivative is just the negative exponential of negative x squared. Because if you take that derivative, we're going to find exactly this expression in here. And at infinity, it's 0. At 0, it's 1 or negative 1. So you'll have 0 minus 1, which is positive 1. So this whole integral becomes just 1. So this integral is going to be 2 v naught over square root of pi. And that expression then gives me v average is going to be 2 v naught over square root of pi. And 2 over square root of pi is just 1.13. So it's slightly more than v naught, that most probable velocity. And actually, if you plug in the square root back into and you rewrite the expression for v naught, the 2 becomes square root of 4. But remember, you have a 2 already. 2 times 4, that's 8. And you have the square root of pi, it comes in. And this expression, again, was given in the book. And you're supposed to do it as part of a homework. And I'm going to show you exactly what homework problems that you're supposed to be doing to get this answer. So we're doing these problems as we're doing this in the lecture, part of the homework problems. So again, this is the average velocity. So if I take all of the velocities and average them out, this is how much they're going to be, slightly more than that most probable velocity. The final thing in here in the puzzle is the RMS value. For the RMS value, we found it already to be square root of 3 kBt over m, but we found it using a different argument, namely that model and all of the arguments and the momentum and the change in momentum, the impulse and all of this argument. And we found at the end, the kinetic energy has to do with the temperature. And we took the square root of the velocity from the average kinetic energy. And we said that must be the RMS value. Now we need to check that to see if this model works. So what we're supposed to do now is to take the square root of the average of the square of the velocity. Again, any average, you multiply by FV/dV, and you square the velocity first, and you take its average, which is this whole thing, and then you take its square root. That's why it's called an RMS. S stands for squaring, M stands for the mean, which is this operation, and root stands for taking the square root at the end of the day. So we're going to do this operation, and if we're careful, we're out change of variables. Now, how many v's we have? F of v already has a v squared in it, times another v squared, that's v to the power 4, times a dv that will have another v in it, v naught in it. So it's going to be v naught to the power 5, times f of v has a c, and the c has 1 over v cubed, v naught cubed. So you'll have a v naught to the power 5 over a v naught to the power 3, cancel the 3 with the 5, and you will end up with a v naught squared in here. Of course, the 4 over square root of pi, and this is a dimensionless integral. Because this is an even number now, so this is going to reduce to the Gaussian. So we keep on doing the by part until we get to the Gaussian really part, which is square root of pi. So that square root of pi will cancel the square root of pi. So do not be tempted by taking the square roots yet. Okay, leave it to the end. So again, by parts, one of this x to the power 4 is going to be x times exponential of negative x squared, and it will be left with an x cubed by itself. So this is going to be the d sub negative exponential of negative x squared over 2. You have seen it at least 2 or 3 times so far today. And by parts, the first part, remember, from the x to the power 4, one of the x's was borrowed for this operation, and the other x cubed remained intact. So here is negative x cubed over 2 exponential of negative x squared between 0 and infinity. At infinity, it goes to 0 because of the exponential. At 0, it goes to 0 because of the power. So this is 0 no matter what. And then the antiderivative in here will pick up a 2. And the negative times the negative from the by parts will become a positive. And this 2 cancels this 4 again. You have seen something similar so far today. And I will be left with a 2 in here. And that's where the 3 comes from, by taking the differentiation of x cubed. That is going to be 3x squared. So the 3 times the 2 that remains from that simplification becomes a 6 v naught squared over square root of pi. And now this integral, you have seen it already by itself. But for the sake of for more practice, we're going to do it again. So we're going to do one of this x squared. We're going to include it in the exponential, and note that this is the d of the negative exponential of negative x squared over 2. And the other x that is remained by itself is part of the integration by parts. So you have negative x over 2 times the exponential of negative x squared. And this again goes to 0 because of the same reasons that its predecessors went to 0. And now I have another factor of 1/2 that pulls up from this integration by part. And you have a 6 in here. 6 and 2 cancel, and I have a 3. And this integral at the end, because I was left with an x, by the way, when I take the integration by parts, it becomes a dx and the exponential by itself. And this, we have seen it to be 1/2 of this integral. And we argued that that is equal to square root of pi. So the square root of pi divided by 2. So at the end of the day, the RMS is square root of 3 v naught squared over 2. Remind you that v naught itself is 2 kBt over m. The 2 in the v naught and the 2 in here cancel. And I will be left with square root of 3 kBt over m, which is exactly what we found from the previous argument. So this is so the models are consistent now. So this looks like it's accurate every way. Obviously, if I keep it in this form, I can write it as square root of 3 over 2 times v naught, which is slightly more than the v naught, which brings me back to the same graph that I was talking about in here. So this is the most probable velocity, that is v naught. It's the same expression here. 1.13 is the average velocity, and the RMS velocity is slightly more than, it's 1.22, okay? So this is the average velocity, and this is the root mean square. This means that this is where the average kinetic energy is coming from, okay? it's worth doing a little bit more calculations to understand what this whole thing. Okay. The most probable, if I find the function, let me stop this sharing the screen in here and share with you a calculator that can do integral for me. So let me share. So I have Mathematica in here. I'm going to define the function f of x right now, because we've been dealing with it time and time again. Are you guys? This is one of the things that I was going to tell you. Really need to be familiar with some of these calculators, because they're going to be very helpful for you down the road. So I'm going to write this expression in here, which is 4 over square root of pi times, this is part of C, by the way. And I'm going to scale this one also by the same factor of V naught. So I'm not going to write V naught in here. So it's going to be x squared. Let's make it explicit in here. Let's declare our intentions explicit in here, so we don't have any ifs or buts about it. Exponential of negative x squared in here divided by 2. And this is my definition of this function. So let's make sure that I don't have any problems. Okay, so let's find the f of V naught itself, the maximum probability. Remember, it's at x equals to 1. So it's going to find f of 1. It's probably going to give me the error function, which is a function related to the Gaussian. But if I do this, it's telling me that the maximum value is 0.83. Okay. How many particles are between 0 and they move between 0 and V naught, or the most probability? So for that, I'm going to integrate. I'm going to get a numerical value. Okay, so I'm going to get n integrate. Okay, the function itself that I just defined, and that's the reason why I defined it, so that I don't have to write it. The boundaries of integration over x between 0 and 1. Remember, this is where the most probable, the most probabilistic, basically, value for this velocities are. And I need to close it one more time for the numerical integrations. So it's telling me that there are 42.7% or 43% of the particles moving with their velocities between 0 and the most probable velocity. That means that the rest, which is 57% of them are moving faster. So that is the distribution in here, okay? So this is basically what this thing is. So what I did in here, I integrated between 0 and 1, the most probable velocity, okay? By the way, the book gives you different values between they take the RMS value and they take half of the RMS value, twice the RMS value, 3/4 the RMS value, and tell you how many particles are. There is a nice table in there that you can look at it, and it's all using numerical integration. There is no way you can do this analytically. So you have to, that's why I'm using Mathematica to help me with this integration in here. Now, I need to find where the value of the function f for f of, again, numerical value, f of the average velocity. Remember, the average velocity was 2 over square root of pi. Came about it, okay? So it's going to be of 2 over square root of pi. That is the argument that, okay, close this parenthesis, close the second parenthesis. So again, this tells me that the maximum value is at 0.83, but when I move slightly to the average velocity, then the intensity of the function f drops to 0.8. Remember, I'm using in dimensions of V naught. Okay, I'm following the same steps that I used it for LaTeX. Okay, that's how I actually graph the LaTeX function, because those values I get them from Mathematica. LaTeX could have done the math for me, but it required some other packages that I was not really interested in implementing. But let's find now how many particles are moving between 0 and the average. I would expect about half the particles. 50% of them would probably be moving between 0 and the average, and 50% will be moving faster than the average. That's what the common sense would tell us. If you find the average, half of the particles will moving slower than the average, and half the other particles will moving more faster than the average. So let's check that. Let's find the integral again of the function that I just defined, which is f of x, which is this whole thing in here. That's the definition of f of x. If you the same function that I defined in the notes. And the boundaries of integration are from 0, again, the variable of integration is x, until we get to that number of 2 over square root of pi. That is actually pi capital P. Mathematica is like C, like a lot of other languages, case sensitive. Close this parentheses, close this parentheses, and close this parentheses. So actually, it's not 50%, it's 53% of the particles are moving faster, from 0 to the average velocity. And only 47% of them are moving faster than that, than the average. Okay, so this is an interesting analysis in here. So let's find the same argument in here when we are at the RMS, which is square root of 3 over 2, by the way. What is the peak of that function f? First of all, it should drop. Remember, it was a maximum supposed to be 0.83. So this should be less. So f of, let's find the numerical. If I don't do this n in here to find the numerical value, it's going, excuse me, it's going to give me some error function. By the way, this thing cannot be handled by mathematics from Microsoft, the other software I used last time to do calculations. So that's why I need a little bit of this thing in here. Square root of 3 over 2. We're doing the RMS now. Okay, close the square function, close the f function, close the numerical calculations. So it's going to be 0.775. So it dropped from 0.83 to 0.8 to 0.75, which is expected. That's how the behavior of this function is expected. Are you guys looking at the mathematics or Mathematica, or am I?
Yeah,
am I sharing my? Okay, good.
Yeah, we can see.
Very good. So n, we're going to integrate now from 0 to the RMS value. Okay. Okay, we're going to do the integration one more time from of the same function f of x. And the boundaries of integration now for x, first of all, from 0 to that square root. In this dimensionless numbers, is in the units of v naught, this is what the RMS value is, square root of 3 over 2, which is 1.22, by the way. Close this parentheses, close this one, and close the last one in here. And it's telling me 60% of the particles are moving from 0 to the RMS value. How about 1.5 the RMS value? So I'm going to copy this, or at least redo the calculation in here, and multiply this number by 1.5. So it's 1.5 times this number. Okay, just to show you that this number increases and increases a lot. It's 92% of the particles are moving with 1.5 the RMS value. If we go to twice this many, it's 99% of the particles are moving from 0 to twice the RMS value. That means less than 1% are moving faster. That's why that graph really did not make sense to extend it way beyond 3 times V naught. Okay, because twice the RMS value is less than 3 actually, because the RMS value is 1.22 times 3. It's still, what is it? 3 point something. Okay, so it's still slightly more than 3. So it really doesn't make sense to extend it beyond that thing in there. Let's make it 3 times. No, 2 times. 2 times is still 2 times 1.22 is 2.2 something. So let's extend it to slightly over 3 to see how many we really missed in that graph. Okay, practically anything. We're almost at 1 in here. As a matter of fact, if I force this to a lower, is it like this? I don't remember. Yeah, if you limit it to 2 digits in the representation or even 4, it's going to tell me it's exactly 1.000000. Unless we go to even a higher precision, then it's probably going to give me something else. Okay. So that is really the idea behind it. So this is the point that we're trying to say in here. Up to the RMS value, you have most of the particles are moving, 60% of them. Twice the RMS value, it was 92% or something like that. Okay. No, twice the RMS value was actually 99%. 1.5 the RMS value was already at that number. Okay. So I hope that you guys appreciate 2 things. First of all, that these 2 theories are accurate. And then the other thing is statistics. Statistics is a wonderful science that tells me a lot about the systems without really doing a lot about them. If you look at your book at page 599, at table 18.2, you will see roughly this numbers in here, okay? And they're V over VRMS. They're scaling with VRMS, not V naught, which is similar. We could have done it, except that the maximum would be shifted on the left if we scaled it that way. And you will see at twice the RMS value, they have it listed at 0.993, okay? Which is 99% if you were slightly more than 99%. And that's exactly what we found, actually. Found 99.27 something, which is approximate to 99.3. So this is really the statistics of this and how fast the molecules are moving and everything else. I'm going to defer the discussions for the equipartition theorem and the calculation of CV, which is the molar specific heat, to the next chapter. The reason why I'm doing this is because of the fact that next chapter really deals with the energy and how the energy changes. And the key word here to remember from this whole statistics business is the internal energy of an ideal gas really depends on temperature, and temperature only. If the temperature increases, the internal energy of the system increases. If the temperature decreases, the internal energy decreases. If the temperature does not change, the internal energy does not change. Okay. So in a nutshell, and this is, we're going to come back to it. Okay. So don't think that this is the full topic. Okay. Using the equipartition theorem, we're going to say that the energy of a system depends, in a sense, on the temperature. And I'm going to introduce CV, okay? If delta T is equal to 0, that means delta U is equal. I'm using U for the internal energy, okay? So delta U is 0. That's in a nutshell what this is. What this CV in here is, what this N, first of all, is the number of moles. Okay. What CV in here is the molar, because it's per unit mole, it's molar. Specific heat, because how temperature changes, okay? And this is in the case when the gas is actually sealed. That is the only thing you can do to it is add heat to it. So that's why it's called heat. At constant volume, that is what the constant volume is. So if you take a gas and you seal its containers, it does not grow or shrink one way or the other, and you add heat to it, the only thing that's going to happen, its temperature starts to increase. Its molecules start to move faster and faster. That's what temperature is, because that's what the kinetic energy is. So the kinetic energy starts to increase all of a sudden inside, which means its internal energy starts to increase. Okay. If the gas is, excuse me, if the gas is monoatomic, then each and every one of its molecules will have its average kinetic energy. This is its average kinetic energy per molecule would be only due to translation. Okay? But I don't have one molecule. I have an Avogadro number of them. I have a huge number of them. I have n of them. So this is for the entire, this is per molecule. But for the entire gas, the kinetic energy will be just 1/2 times the number of the molecules times m times VRMS squared, which means that this is 3 times the number of the particles times kBt. And the number of particles, n, is equal to the number of moles times Avogadro's number. Remember, Avogadro's number is 1 mole, but I really don't have necessarily 1 mole. I could have an n number of moles. So this can be written as the average kinetic energy then for the entire gas is 3/2 times the number of moles times Avogadro's number times Kb times T. And this is R. That's how we define Kb, by the way. So this is nRT. Okay, so this is how much change. This is how much change actually. I'm assuming that temperature has changed. Okay, so there should be a delta everywhere in here. Okay, so this is how much change in the kinetic energy went, which is the energy of the system. So this is how much energy has changed in the gas. End of the story. If the temperature was under those conditions. So therefore, this is equal to n times CV times delta T. That's by definition of this process, because we're doing this one where the volume has been fixed. This container does not change shape, it retains its shape. So this is at constant volume. That's what the CV stands for in here. That's what the V stands for in the CV. Obviously, from this expression, CV is equal to 3/2 R. This is provided that the gas is a monoatomic gas. Now, if the gas is not monoatomic, let's say it's a diatomic gas. Then each degree of freedom for that molecule will bring not 3/2 of kBt, but rather it's going to bring 5/2 of kBt. Because if I look at a diatomic gas, okay, it can move in the x direction, can move in the y direction, and it can move in the z direction. Those are 3 degrees of freedom, but it can spin this way or spin that way. Okay, spin this way or spin that way. This spin will have a 0 moment of inertia, so there will be 0 contribution to the kinetic energy. This one will have 1/2 of I times omega squared, and this will have 1/2 of I times omega squared. So both of them will contribute to the kinetic energy, and each degree of freedom will change. So we're changing the model now because we did not know about this detail when we did the model. So we're thinking, because each one of these 3's came about from one component of the velocity and the kinetic energy, because we're adding 2 more. So now, instead of whatever 3 was, it's going to be 5. So the specific heat now, the molar specific heat in this case is going to be 5/2 R. That's it. In the case of a solid, it's going to be slightly different actually, because there is vibrations, and even the molecules, they don't move too fast on the x direction because of the short range interactions that they have with one another. So now all of the CV in the solid is actually going to have, there is a vibration in addition to that, and it's going to be for a solid, it's going to be 6/2, which is 3R. Okay, so this is for a diatomic gas. In general, it's going to be a formula of this form. When you have polyatomic gases, like for example CO2, okay, or NH4, okay, whatever ammonia or whatever gas you have to take into account, CV is going to be slightly more, and it's roughly, okay, it actually depends on how many degrees of freedom that you can take, how many vibrations you can include. it's going to be about 7/2R, okay? Or some number around that figure. No, 7. Yeah, it's about this number, okay? Don't quote me on this. It depends. Let's put it this way, depends. But for sure, it's going to be more than 5/2 of an R because more degrees of freedom are involved. So I did not really want to go into detail, yet I want, okay? On Tuesday of next week, when we come in, we're going to find another kind of a process that involves CP, actually. This is the molar specific heat at constant V, at constant volume. We're going to define more processes down the road. We're going to find in particular this molar specific heat at constant, instead of V, you guessed it, to be P, which is pressure. And there is a nice relationship between the two of them, okay? So chapter 19 now gets into, first of all, we're going to introduce the first law of thermodynamics and then get into all the nitty-gritty of these things and how to calculate them, okay? Sounds promising. Can we get into the problems now?
Let's do it.
Okay. Okay, so let me first of all, hopefully you guys have your books open with you guys. Okay, problem 1873. We just did it in part of the lecture, except that it's a lot easier for you with problem 1873 because it gives you the integral, no matter what n is, as long as n is integer. Okay, and it's trying to find v square f of v dv to show that it's actually the square root of 3kbt over m. So that is problem 1873. It's done. So you mark it as done, but please go through the steps also to make sure you know how to do it again. Okay. Same thing. Problem 1876 is also, you can mark it as done. That's finding the average velocity. That we also did it in lecture. But that is actually a lot easier in this case than having done it in lecture, because if they give you an integral in here of the form x to the power n over exponent. Actually, if n is not an integer, this is the gamma function. But n is an integer, the gamma function reduces to the factorial. Gamma function is just an exponential expansion of the factorial function. But they give you that, so you can do this. So this is, but you already we already have done in the lecture. You guys agree that problems 1873 and 1876, they're done for?
Yeah.
Okay, so the other problem of interest to me is 1868, which I'm going to do briefly with you guys. You are supposed to finish this problem. So part of the discussion item in here, you are supposed to finish problem 1868. Okay. The other problem that caught my attention is problem 1883, which is fun problem. 1878, I expect you guys to understand how to do it because it's just graphing tables. And at some point, I'm going to pull Excel and I'm going to pull actually a GeoGebra to help you guys do graphing, because graphing is part of this class. So you really should be able to, if you have not mastered how to graph functions by now and find the R-squared value and the fitting of graphs and things like that, this is something that you should really have known by now. If not, we're going to do this in this class. Okay. The Leonard-Jones potential, which is problem 1867, is a typical problem where you have encountered it probably somewhere in the past when I try to remember, at least physics 1. But it's just, it gives me a model basically for how molecules are basically bound together. Okay, we probably are going to revisit this problem down the road. So 1868. So I expect that you guys have the book by now, and you're looking at problem 1868, because this is a simple application. Doesn't matter in terms of strength, it has 1 point in there, so it's an easy problem to do. 1868. And this is on page 609. It says, what is the total random translational kinetic energy of a 5 liter? So the volume is 5.0 liters of hydrogen gas. Hydrogen gas, not hydrogen atoms, okay? Which means H2, with a molar mass of 2.016 grams molar of 2.016 grams per mole. I have the periodic table in here, and if you look at the hydrogen in here, oops, hydrogen in here, it says 1.008. So you have to multiply that by 2 to get the molecule itself, because you have H2, okay? And you're wondering why there is a 008 in there, and because there are isotopes other than the normal hydrogen, okay? So with a pressure of 1.01 10 to the power 5 Pascal. So there is a mixture of units in here. So this is in SI, this is in grams, so we better convert it to kilograms. This is in liters, so we better multiply it by 10 to the power -3 to get it in cubic meters. Because 1,000 liters is a cubic meter, okay? And the gram, we have to multiply it by 10 to the -3, again, to convert this one into a kilogram per mole. So we're going to be careful enough with the units. And the temperature is 300 Kelvin. I'm going to give you a break between the lab and the lecture, okay? So we're going to take a break after we do at least this problem, okay? So what is the total random kinetic energy? Well, in this case, the total, not per molecule, okay? The total. I remember the per molecule is 3/2 of kBt, okay? But we want the full shebang. We want the whole thing. So this is per molecule. And we want the whole thing, so we better multiply it by the whole number of particles, which is 3/2 of kBt. And that is going to be, remember N, I just wrote it to be Na times the number of moles. So it's going to be the number of moles times 3/2, Na times Kb, that's RT. Well, I don't know what the number of moles is. I can assume it's 1, but it's not probably true. So, but I know P, I know V, I know T. I can use PV equal to nRT. Okay? From here, we can find the number of moles, which is P times V over RT. Plug in the numbers in here, gives me the average kinetic energy, the total, not per molecule, everything, the whole thing is going to be N, which is P times V over RT times 3/2 of RT. They might as well not have given us a temperature, because as far as this thing in here is concerned, they cancel out. So it's 3/2 of PV. We have P, which is 5 liters, or 5 times 10 to the -3 cubic meter. I mean V, that is V. V is 5 times 10 to the -3 cubic meters, I'm sorry. And then we have P, which is 1.0110 to the power 5 Pascal. Multiply the two, and you can find the average kinetic energy. So you know what to do now. Make sense?
Yep.
Yes.
Yeah, it makes
Okay.
sense.
So this is so easy that even I can do it. Okay. If the tank containing the gas is placed in a swift jet moving at 300 meters per second, what percentage of the total kinetic energy of the gas has increased? Obviously, if we take this 5 liters and put them in a jet moving with a speed v of jet equals to 300 meters per second, this is a subsonic plane because the speed of sound is 340 meters per second, and this is moving just below the speed of sound. Okay. So what percentage? We need the mass of these things. Okay. We need the mass of the gas, because the new increase in kinetic energy, if you wish, due to the motion of the jet of the entire gas is 1/2 of the mass of the gas. Let's put it big M, okay, just to make a distinction between these masses, times the velocity of the jet squared. We have this is 300 squared. We need the mass of this gas, how much it is. Well, we have the number of moles. Which is PV over RT, okay? And we know the mass per mole. And the mass per mole is 2.016 times 10 to the negative 3. So the mass as a whole is just the number of moles times the mass per unit mole. And this should give me the total mass in kilogram, by the way. But remember, this is P times V over RT. Now we need T. Without T, we cannot find this thing. Times 2.016, 10 to the negative 3 kilograms. Plug in this times V squared, and you should find the kinetic energy due to the motion of the jet, which should be 1/2 times PV over RT times the molar mass, which is 2.016 times 10 to the negative 3. I'm using SI. So the energy is going to be in joules times velocity of the jet squared. You are expected to finish this part, okay? And then find the two ratios, because they want to find how much has changed. So the change in the kinetic energy divided by the initial kinetic energy. So that should be 1/2 of PV over RT times the molar mass times the velocity of the jet squared over that kinetic energy. And that kinetic energy, if you guys remember, is 3/2 of PV. So this is 3/2 of PV. Cancel the PV, cancel the half. And the ratio should be equal to 2.016 times 10 to the negative 3 times the velocity of the jet squared, which is 300 squared, divided by 3 times R, which is 8.314 times 300 times the temperature. One of this 300 cancels at 300, and the numbers, if I'm doing it, okay, should be about 2.016 times 10 to the negative 3 times 300 divided by 3 times 8.314. 3 cancels this 3. The 100 cancels this, and I would be left with a -1. So it should be about 0.2016 divided by 8.314, which is roughly about 2/8, which is 25%, but it's going to be 0.25%. It's going to be about 3%. Okay, this is my estimates. I cannot guarantee their accuracy. So you're supposed to check that, also part of your assignment today. Make sense?
Professor Busidi, what happened to the temperature on the denominator? Because we have it as 3 times 8.314 times 300. What happened to the 300 on the bottom?
The velocity of the plane is 300 squared. I mean 300. One of the 300 canceled that 300.
Oh, okay, got you.
That's my estimates. Okay, don't quote me in here. From this point on, it's at your own risk.
Right.
Okay.
Right.
Okay. So guys, from this point on, you're supposed to don't trust me. Okay. So take it on your own risk. So I'm saying 3%. You might find it more than that, okay, or less than that. So it's up to you. So check it on your own. Okay. by what percentage is the total kinetic? So that's what I'm saying. It's about 3%, okay? Since the kinetic energy of the gas molecule is greater when it is on the jet, does this mean that the temperature has gone up? Obviously, since the plane now is moving, although albeit it did not increase it according to me by that much, by 3%, the kinetic energy on average was much, much higher to begin with than with this additional motion of the plane. Does this mean that the temperature somehow has been affected, that somehow it's going to get hotter? Yes or no? And why? Can I have some takers who think that the temperature now will increase? Because look, remember, the whole argument is that the kinetic energy is related to the temperature. So the kinetic energy was this much, okay, to begin with. And you can calculate it, okay, which is 3/2 times RT, okay, to begin with, okay? Now you put the whole thing in a plane and you take the plane zooming almost with speed of sound, okay? So the kinetic energy has changed. It's not the same anymore, okay? Does this mean that the temperature has increased? Because the temperature and the kinetic energy, they go one by one.
It would
Or,
increase.
okay,
I
who
agree.
thinks? Okay, good. Anybody else?
Yeah, I agree, because technically, if the plane is moving faster, and we said that kinetic energy is proportional to the temperature, that would mean that as the kinetic energy would increase, so would the temperature, correct?
I'm asking, so don't ask me. That's the question. Let
But
me
if we're
tell
talking
you.
about the internal energy, didn't you said that it doesn't include the kinetic energy of the entire body, just like the individual molecules? But the kinetic energy of the individual molecules isn't changing, so the temperature wouldn't change?
No, actually, the first part of your argument is incorrect, but the second part may be correct, okay? The first part is the kinetic energy, the random kinetic energy of motion of the molecules, they add up to the kinetic energy in here of all of the, basically. So that is the total kinetic, that's 3/2 of RT. But the second part, you're right on it, okay? So those of you who think that the temperature will increase is wrong. It's not going to increase. It's going to stay the same. Even if the plane is moving supersonic, the temperature is not going to change. Although the kinetic energy should be impacted somehow by this motion.
And that's because each of the individual molecules aren't changing their kinetic energy?
The whole gas is changing. So you're right on that part. Okay? The whole gas is changing. Okay, it has an internal energy which is 3/2 of RT, but as the plane moves in one direction, this is not random anymore. The key word in here is random motion. So you're absolutely right, Maddie, on the fact that the random motion of the molecules is not impacted by the motion of the plane. So the temperature remains the same. So the key word is random. So the first one that we have found was due to the random motion, meaning molecules going every which way, but now it's an organized motion. So the whole thing is moving in one direction, the direction of the plane where it's moving. So that's why the temperature should not be impacted. Because those individual molecules add up to the kinetic energy of the average kinetic energy of the whole gas, all of the molecules basically put together. And at the end of the day, that is a random motion to impact the temperature. Okay, so the answer to the first part is no. The temperature does not increase because the temperature is due to the random motion, the model that we used before. Good. Makes sense now?
Yeah, now it makes sense.
Okay, very good. So I trust that you guys are going to finish the numbers in here and make sure that it makes sense and see if that percentage holds true. And we're going to meet. I know we went about 5 or 7 minutes, or probably 10 minutes more than the allotted time for this lecture. And because I know that we have a lab after that, so I'm going to give you about 15 minutes break. So we're going to meet at 9:45 from now. So you can go and eat, drink, whatever you want to, use the bathroom if you want to, and we'll meet again in about 15 minutes, 9:45. Make sense?
Sounds good.
Yeah, sounds
I'm
good.
not going to close the
good.
session. I'm not going to close the session. All I'm going to do is stop the recording and leave the session open so you can turn off your microphone and the video if you want to, and then come back around 9:45. Oh, I don't want to cancel. Hi, everybody, and welcome to After the Break. I'm going to thank you, Helen, although your microphone is off. I'm going to continue these problems in here. The second problem that is actually of interest is problem 1870. Problem 1870 is kind of an easy problem that you guys can also do, okay? Problem 1870, it's from the same page, 609. It says that the surface of the sun has a temperature of about 5,800 Kelvin. So that's the temperature of the sun, and consists mainly of hydrogen atoms, okay? That's really typical of any star. It's the main composition of stars is hydrogen. Let me see if I can get this notes back up. Share. I hope that you guys are writing these things and you have at least your notes with you and your book with you to be able to do all of these problems, because come test time, you're accountable for all of these examples, for the homework problems and things that we do. So the second problem I'm talking about is problem 1870 from the same page 609, okay, from the book. And it says that the surface temperature of the sun is about 5,800 Kelvin. Okay. And it's mainly made out of hydrogen. Find the atomic speed of the hydrogen atoms at this temperature. So hydrogen atoms, okay, not hydrogen molecule, not H2, but H by itself, okay? Because at those temperatures, the hydrogen breaks down and so on and so forth. So the mass of the hydrogen in this case atom is about, according to the table I have seen you, or divide that number by 2, it's 1.008 grams per mole. Okay. So you have to multiply this one by 10 to the negative 3 to get the mass in kilogram. The average, so the first part in here is the atomic speed of a hydrogen atom, of a single hydrogen atom. So a single hydrogen atom will have its VRMS, okay, equal to square root of 3 times KB times T divided of the mass of a single hydrogen atom, which should be 1.008 times 1.67 times 10 to the negative 27 kilograms. Okay, so this is the RMS speed with which the atoms are moving. So it's going to be 3 times 1.38 times 10 to the power negative 23, that is KB, times T is 5,800 Kelvin, divided by 1.008, if you care to really take that many precisions, times 1.67 times 10 to the negative 27. So it's going to be moving super fast. Okay, so 10 to the negative 27 and 10 to the negative 23, I'm down with 10 to the negative 4 in the denominator, so it's going to be upstairs. So it's going to be 3 times 1.38 times 5,800 times 10 to the power 4, because they took it out to the numerator, divided to 1.008 times 1.67. I'm kind of curious about this RMS speed myself. That's why I want to do it in here. And let me share with you the same calculator I've been sharing with you today. So let me share with you. This entitled. So it's a square root. Let me get the numerical value. Although it has decimal points, so it's going to give me the numerical value no matter what. Square root of 3 times 1.38 times the temperature, which is 5800 Kelvin, times 10 to the power 4, which is 10,000, divided by, open parentheses, 1.008 times 1.67. Close this parentheses, close this one, close that one. It's 11,000 kilometers, 11,943 meters per second, or 11.9 kilometers per second. You have to be very, very, very careful when you're doing speeds, when calculating speeds, okay? That's why you have to include this one. If the speed turned out to be more than a certain number, which is 300,000 kilometers per second, or 300 million meters per second, at that point, you have to immediately stop from what you're doing. Because that speed is exceeding the speed of light. That means there is something wrong with the problem that you set it up with. Because when you're dealing with this much powers, when you're dealing with these things, you could end up with a number if you forget to divide by something or add something, or you forgot to that 10 to the negative 23 in the numerator, you end up with 10 to the negative 27, which you take it upstairs is going to be a huge number. So you could end up with a velocity by error more than the speed of light. At that point, either there is something in the algebra or there is something in your theory. Because chapter 37 is coming down the road, nothing can move faster than the speed of light. If it does come anywhere close from the speed of light, the physics has to change, okay? The physics has to change. I don't know if you did this problem or not in physics 2, but there is a fascinating problem in physics 2 when you do the cyclotron motion and you start plugging in numbers left and right, and there is a potential where the proton actually, as it's moving through the cyclotron, the accelerator, you could end up with a with a speed that is faster than the speed of light, which means that there is something, there are some limitations. Actually, cyclotron will never go faster than the speed of light. And as a matter of fact, it doesn't even reach it. The betatron actually can get you speeds that are very close from the speed of light, but even then, the charged particles, the proton or whatever you're trying to accelerate, starts to radiate energy, in which case they cannot even reach the speed of light. So there is practically no way that you can get that. So that's why I was kind of curious, because I want to know that this number, which is in meter per second, 11,943 meters per second, is less than the speed of light, which is 11.9 kilometers per second. It's slightly more than the escape velocity from the Earth, which is 11.2 kilometers per second. So that's this problem 7, part A. So they gave you the mass of the that. So the escape speed for a particle leaving the gravitational influences of the sun is given by, you guys remember from your physics 1 discussion, let me stop sharing this screen and go back into my notes. Share. That a particle with a kinetic energy 1/2 of mv squared inside a potential that is given by g times m times the mass of the star or planet or whatever it's trying to escape from, divided by r. This is the potential. This is the kinetic. If the kinetic is at least equal to the potential, that object may escape. Hence, that's how the escape velocity was defined from physics 1. is equal to G times M over R, where R is the radius or whatever you're trying to escape from. That's why this escape velocity does not depend on the mass of the object, because the mass cancels and you will only be left with the mass you're orbiting trying to escape from, like the Earth for the case of the Earth or the Sun for the case of the Sun. So the escape velocity is equal to the square root of 2 times G times the mass of the Sun divided by R. And this formula was given to you, so I really did not need to prove it, as long as you have taken physics 1 and you know where it's coming from. And that is where it's coming from, okay? So where M is the mass of the Sun, its radius R, and G is a gravitational constant. Using example, whatever, use F to find. So we need to find the escape velocity because we want to compare these two numbers. In other words, can this molecule escape the Sun? So let's do that. The escape velocity is equal to the square root of 2 times G. G is 6.67 times 10 to the negative 11 times the mass of the Sun, which is roughly about 2 times 10 to the power 30, okay, divided by the radius of the Sun, which is about 700,000 kilometers. 696 actually, 1,000 kilometers. And 1,000, that's 10 to the power 5, 10 to the power 3, because you want it in meters actually. So 700,000 times 10 to the power 3 to convert it into meters. So if I didn't make any mistake, I really want to find what this number is. The first thing that you really need to do is handle the powers when you're dealing with numbers like this. 10 to the negative 11 and 10 to the power 30 is 10 to the power 19. 10 to the power 19 and 10 to the power 8. So you're left with 19 minus 8, that is 11. So we're left with 10 to the power 11 under the square root. 2 times 6.67 divided by 6.96 times another 2 coming from the mass of the Sun times 10 to the power 11 under the square root. And again, I'm curious to find this number because I want to compare the two, first of all, but also I want to make sure I don't have some nonsense numbers in here. So let me stop sharing. Let me move this slightly to this screen so that I can see what the numbers are before I plug them in. Let me share. What is the share button? Share the calculator. Okay, so again, with decimal points, we don't worry about this part, but I want to make sure. So I have 2. I'm trusting that you guys have your calculator also working, okay, because you don't rely on my numbers, okay? Especially the mass of the Sun is not exactly 2 times 10 to the power 30. I think it's something times 10 to the power 30. Okay, times 10, times 2, another 2 again, times 10 to the power, open parentheses, no, you don't need to, 11, no, maybe we should. I think it's just, although this also works with the spaces too, so I think it's gonna read it correctly. Divide by, what do we have in the denominator, 6.69, 6.96. So if I did not make any mistake, this is the escape velocity. Oh, I'm sorry. There is a 10 to the power. Oh, no. There is something I forgot in here. Sorry, guys. It's under the square root. Yeah. Okay, that's better now. 10 to the power 11 meters. That's way more than the speed of. You see, I rest my case. Okay, about what I told you should be careful with. Okay, I fell into 600,000 meters per second. 620,000 meters per second, or 620 kilometers per second. It's still a lot less than the speed of light, by the way, because the speed of light is 300 million meters per second, or 300,000 kilometers per second. This is just a fraction of that number. So these things are well held into. So even with the 5,800 Kelvin, 5,800 Kelvin, yes, and they're moving super fast, 12 kilometers per second. 12 kilometers per second is not anywhere near the escape velocity from the sun, which is 620 kilometers per second. Okay. Does this problem make sense to you guys?
Yeah, it does.
Okay, very good. Can appreciable quantities of hydrogen escape from the sun? Obviously no, because I mean, the RMS is even if twice the RMS, which is at 99%, which is about 22 kilometers, 24 kilometers per second, 3 times, which is practically negligible. So practically there is no hydrogen is leaving the sun with this speed. Okay, so the first, second, can appreciable quantities of hydrogen escape from the sun? No, no appreciable. Negligible, maybe, and so much negligible that you cannot even think about it. Okay, because the ratio of these two numbers, 620,000 divided by 12 is, wow, man, I hate, that's why I do this. Just gonna put a decimal point in here somewhere. Now it's giving me a number, 51,000 times. Okay, this will put me way back on that that graph that I showed you guys. Okay, now here is the point to remember. Yes, can they escape? Is there any? What is the other? What is the problem first? Okay, can any hydrogen escape at all? Yes, practically nothing according to this theory. But there is other mechanism for hydrogen to escape. Okay, so there is other ways for hydrogen to escape during the because of the other phenomenon other than this one. Like for example, when magnetic fields are involved, and there are tremendous magnetic fields are involved, and those solar flares that form, those they will cause actually a huge number of elementary particles that leave, mainly hydrogen, mainly protons, electrons. Okay, and that is what the solar flares are, and that is what can cause a lot of problems for us. Okay, so I hope that you guys are enjoying these problems as much as I am. There is another problem that I'm going to share with you, and that's going to close the book on the problems, and we're going to delve into the lab. And problem is 1883. We move this to this side, otherwise it cannot write on it. Share. (1883), and that is from page 611. And the reason why I mentioned this problem is for 2 reasons. First of all, it's related to the topic we're discussing, so that's reason number 1. Reason number 2 is the 21 centimeter wavelength. You can Google it if you want to. This is a big deal in astronomy. This is basically what cold hydrogen has been emitting waves at, and we're going to come back to this problem down the road because of a special configuration of the hydrogen atom itself. You have an electron moving around the proton, and the electron can have the spin up or down, and because of the way that it's basically excited by the stars behind it, so the spin of the electron flips, and as it flips, it's going to emit energies in this wavelength. And this wavelength is not in the visible, of course, the visible extends all the way to 700 nanometers, and that is a very short wave. It's about 0.7 or about 1 micrometer, and micrometer is a lot less than a centimeter. So this is a very, very long wavelength, very low energy, okay, emissions, and they happen to be not even in the infrared. They are actually in the radio range, or at best in the microwave region. So this technology that enabled us to look at the sky. So tonight, let me get stellarium going. So tonight, when you go and look at the sky, I hope that you will appreciate this thing in here more. And look at this problem in here. So problem 1883, which is from page 611, says that they give you a picture, which is a dark nebula. share with you. Stop sharing that screen and share with you this software to give you a better share. Stellarium. So this is how the night looks like right now. I'm going to come in here. I'm going to change the time to night, sometime around 10 p.m. Okay, that's fine. And furthermore, I'm going to stop this. And we're looking at the south in here. Look at the regions of the sky. Man, I cannot even see anything in here. Because of the horizon, can you remove the city lights? Effects of the atmosphere. So this is my point in here. There are a lot of dark regions in the sky in here. And when you start zooming on them, you'll start pulling all kinds of objects in them, okay? But the point being in here is there are regions, if you look at the Milky Way, which is here, this is Sirius, by the way, this is where the Milky Way extends in here. There are actually more, southeast, there are more objects in there, and there are, no matter even this point in here in the sky, there are all kinds of objects in it. So the point being in here is, one of the things that can explain those dark regions was this. Let me stop sharing. Let me go back into my notes, because we're not doing astronomy, by the way. We're not doing math either, so don't go and start claiming that we're still doing physics, hopefully. So, so if you look at the picture, there are dark regions of the night sky that are extremely dark because they are mainly hydrogen atoms, not hydrogen molecule. Again, it's not H2, it's H, okay? The same molar mass that we were discussing up to this point. And they have a high concentration. And when we say high concentration, it's relatively speaking. Those numbers we've been dealing with so far, they're of the order of Avogadro's number over a certain finite volume. This one now, the number of particles of hydrogen over is about 50 hydrogen atoms per unit volume, per cubic centimeter, actually. Per cubic centimeter. So this is a very tiny number, okay? So this is N over V. Relatively speaking, it's low density because the entire space is low density. But this is actually high concentration. That means every cubic centimeter. That means every meter, and this is, by the way, a mistake that even at times calc-based students make. A centimeter is 10 to the negative 2 meters. But don't forget to cube this number. That is what the mistake is. So when I say 10 to the negative 2, I mean per cubic centimeter, is 10 to the negative 6 per cubic meter. So it's going to be 50 times 10 to the power 6 per cubic meter. Obviously, if I take a centimeter, which is this much, and I find 50, if I take cubic meter, I find the number multiplied by a million. So it's cubic meter is a large number, but it's still a lot less than the Avogadro's number we've been dealing with. So it's still very low density, okay? So a typical dark nebula is about 20 light years, so in radius. So from here to here, it's about 20 light years. And 1 light year is, they gave you the conversion, is about 9.5, 10 to the power 15 meters. How much, what's the distance the light travels in 1 year? That's basically what the question is. Light travels in every second 300,000 kilometers. And if you multiply second by that by 3,600 to find how many an hour times 24 to find out in a day times 365 to find how many in a year, this is the number you end up with. Okay, so this is the size. It's a huge size. Okay. A, estimate the mean free path of the hydrogen atom in a dark nebula. Of course, they gave you also the temperature, which is very cold. That's why it's called it's in the atmosphere. Of course, it's hotter than the remaining of the universe. The remaining of the universe is about 3 Kelvin or less. So this is 20 Kelvin, which is super cold compared to our daily experience, but it's still super hot, okay? Find the mean free path. For that, we're going to use the expression that we found last time, which is somewhere in the notes from the top, way back up. And no, it's actually before. Here is the expression. So lambda turned out to be V over N times 4 times square root of 2 pi r squared, where r is the size of those particles. For this case, it's the hydrogen atom. And they give you the size of the hydrogen atom is about 5 times 10 to the negative 11 meters, which is about half an angstrom. Okay, so we're going to use that expression for lambda equals to V over N times 4 pi times the square root of 2 times r squared. So it's straightforward because lambda is equal to 1 over n over v, and n over v, we have it. We have n over v, which is 50 times 10 to the power 6 in SI units. 4 pi, which is a constant, times square root of 2, which is constant, times r, and r, they tell you, is 5 times 10 to the negative 11 meters. Or typically, this is how I remember it, half an angstrom, and an angstrom is 10 to the negative 10 meters. It's the same thing, okay? So they gave us this number, which is 5 times 10 to the negative 11 squared. So if you plug in all the numbers, 1 over 50 times 10 to the power 6 times 4 times pi times square root of 2 times 25 times 10 to the power 22 with a negative sign, okay? 22 and 10 to the power 16 is 10 to the negative 16. And then you work out the numbers later on. So 2 times 25, that's 50, times 50, that's what, 2500? And you'll be left with 2 square root of 2 times pi. So as a shortcut to your calculations, this is what you're supposed to have. 10 to the power 16. It's in meters, by the way, the answer, okay? Because everything else in the SI. So 50 times 50, that's 2500, times 2 times square root of 2, because I borrowed one of the 2's to make this one 50. And then times square root of pi. It's going to be a huge number. That means these atoms will never meet. I mean, they hardly meet. I shouldn't say they. It turns out, let's find this number because I'm kind of curious also trying to see what this number is. Can you guys check this number quickly? So 10 to the power 16 over, open parentheses, 2500 times 2 times square root of 2 times, oh, since I have another square root in there, square root of pi, what is square? No, there is pi only. There is no square root of pi in the formula. Okay, times pi. Oh, close these parentheses. Close nothing. No, I don't have any other parentheses. So it's giving me 4.5 times 10 to the power 11 meters. So the lambda is 4.5 10 to the power 11 meters, or 4.5 times 10 to the power 8 kilometers, or 450 million kilometers. That's the separation between that. The distance between the Earth and the Sun, 1 AU, is 150 million kilometers. That's how far the sun here and the earth is here. This distance is 150 million kilometers. 450 divided by 150 million is 3 times. So the distance between the earth and the sun, you go another one and you go another one to find them. So this is where Venus is. I mean, where Mercury is. This is where Venus is. This is where Earth is. This is where Mars is, just before the 2 AU. It's a 1.89, and this is where the asteroid belt is. Jupiter is sometime in here, about 5 times the AUs. If you put one hydrogen atom in the center of the sun, the other hydrogen atom will be at the asteroid belt. This is the mean free path. This is how far close they can come from one another. So this is very unlikely that they will collide. Make sense? These numbers?
Yeah.
Okay. It's fun when you do these problems and you see what they mean, okay? And then estimate the mean free path. Okay, we did that. The radius of the atom. Estimate the RMS speed of the hydrogen atom. Well, the RMS speed is easy to find for the hydrogen atom. The VRMS is square root of 3 kBt over m. Again, we have square root of 3 times kb, and kb is 1.38 times 10 to the negative 23 times the temperature, which is 20 Kelvin. It was given to us in the problem, divided by the mass of the hydrogen, which is 1.08 times 1.67 times 10 to the negative 27. Plug in all the numbers, you're going to find the RMS in here. Again, you have to be careful. Let me put the calculator, and hopefully you guys, you have. Again, try to do the power first, okay? So this is 10 to the negative 4. When you take it upstairs, it's going to be 10 to the power 4. So I'm going to be doing it easier this way. So it's going to be s square root, the first part, open parentheses, of 3 times 1.38 times 20 times 10 to the power 4 divided by, open parentheses, 1.008 times 1.67. Close this parentheses and close the overall square root. And it's saying it's 701 meters per second. This is how fast they are moving, 701 meter per second. So this is their speed, okay? From here, we can find the next one. If it's not asked, we can find it, namely the mean free time. Because we have the distance, we have the velocity, so we can find the mean free time. So we found that based on this result. Do you think that, no, where is it? Estimate the mean free path of a, so we found that, estimate the RMS speed of a hydrogen atom and the mean free time. So they asked it in the same question. Since we have that, then we know that the wavelength is VRMS, not the wavelength, I'm sorry, should not have said that. It's the mean free path, because lambda is always the wavelength, times the mean free time. So from here, it's just this ratio of lambda over VRMS. Okay, and lambda, we found it to be 4.5 times 10 to the power 11 meters divided by the VRMS, which is 701 meter per second. And you can find how long it's going to take. Even if I reduce one of these 2 powers. Okay, so it's going to be dropped to 10 to the power 9. And this is divided by 7.01 or 7, okay? 4.5 divided by 7 is what, about 6 times. So it's going to be about 6 times 10 to the power 9 seconds. About, not exactly, seconds. And that's a lot. That's a lot. Meaning, if I have to divide it by 3600 to find how many hours that is, and it's still, because of the 10 to the power 9, and I have to divide it by 24 hours to find how many that is in days, how many days that is, and I have to divide it by 365 to find how many years that is. So that is the number of years. So convert it back into years. Okay, and you should find a huge number. You have to wait for a long time before two hydrogen atoms get close from one another, even though they barely touch one another on the top. They have to really get into a head-on collision to somehow, with this much kinetic energy, which is 1/2 times their mass times their velocity, to overcome the electrostatic repulsion and then fuse to form hydrogen molecule, I'm sorry, H2. So it takes a long time for this collision to happen. Not as frequent as you might think. Okay. And then we did that. Based on this result, do you think that the atomic collisions, such as those leading to H2 molecules formations, are very important in determining the composition of the nebula? No. Still, because this is very unlikely, takes a long time for them to even collide, and even longer to collide in the proper direction so that they can form hydrogen molecule. Okay. Estimate the pressure inside the dark nebula. They give us P. They give us everything. I mean, they didn't give us P, so we want to find P. Remember, PV equal to nRT. And N is N times Avogadro's number, divided by Avogadro's number, that is, times T. This is KB. So they want the pressure. The pressure is N over V times KB times T. We have everything. This is 50 times 10 to the power 6. We have KB 1.38 times 10 to the negative 23. And we have T, which is 20 Kelvin. So it's for you guys to finish this part. So you should find a very tiny pressure, although 10 to the power 6 in here, but you have 10 to the negative 23. So this is 10 to the negative 17, 20 times 1.38 times 50. So 2 times 5, that's 10. So this is 1,000 already, times 1.38. 1,000 with 10 to the negative 17. So that's going to drop you to 10 to the negative 14. So it's going to be 1.38, 10 to the negative 14 Pascal. Wow. I did it even without a calculator. So the pressure is 1.38, 10 to the negative 14 Pascal. Tiny pressure. Okay. Compare the RMS speed of a hydrogen atom to the escape speed of the surface of the nebula. Assume spherical of the space around the nebula were a vacuum. Would such a cloud be stable or would it not? So we need to find the escape velocity. Remember, it's a spherical shape. That means its volume, the entire volume, is equal to 4/3 pi r cubed, where r is equal to 20 light years. That's how much r is, okay? And so we want to find the escape velocity from here. Again, I wrote the formula earlier. So the escape velocity is going to be the square root of 2 times g times the mass divided by r. R is the radius of everything, but I don't have the mass. The mass is equal to the density times the volume. And the density is that of the times the volume. The density, we have it. We know how much we have m over v or n over v. So this should give me rho multiplied by the molar mass, okay, by the mass, which is 1.08, I'm sorry, times 10 to the, times 1.67 times 10 to the power negative 27. So this is how many kilograms per cubic volume we have. So we have the density, okay? And this number is 50 times 10 to the power 6. So this is the density in number of particles per volume, number of hydrogen per volume. But each one of them has this mass, 1.008 times 1.67 times 10 to the negative 27 kilogram. So this should give me, when I multiply it by this one, how many kilograms per cubic meter I have in this whole thing. Multiplied by the volume of the entire nebula, I will get the mass. So this expression look like this then. The escape velocity then is equal to 2 times 6.67 times 10 to the negative 11, that is the constant g, times the mass. The mass is this number, 50 times 10 to the power 6 times 1.0008 times 1.67 times 10 to the power negative 27 times 4 pi over 3 r cubed divided by r. So there is an r in the denominator, and there is an r cubed coming from the volume. So I'll be left with an r squared times then 4 pi, this is times, there is no denominator, everything is continuous, okay? Over 3 times r squared. And r squared is that 20 light years, 20 times 9.46 times 10 to the power 15 squared. You're supposed to find the square root and make sure it's less than 300,000 kilometers per second, and then compare it to the 701 meters per second that we found, the thermal agitation, the random velocity that we found, and you're going to tell me if it's a volatile or not. It should be volatile. The speed, this escape velocity should be less than, this escape velocity should be less than 700, meaning it's not stable, meaning it's losing its composition, okay? So finish this part. It's not a denominator, this is a continuation, okay? Okay, so it's this part multiplied. And you're going to find, the whole thing is of course under the square root. You're going to find the escape velocity. It should be less than the 700 meter per second for the thermal agitation, for the RMS, which means then that this is not going to be stable. Let me just finish this problem. And if you guys have difficulty with it, please let me know down the road, okay? The other thing in here, it says that the stability of the dark nebula is explained by the presence of the interstellar medium, ISM, an even thinner gas that permeates the space and in which dark nebula are embedded. Show that the dark nebula to be in equilibrium with the ISM, the number of atoms per volume, N over V, and the temperature are related to this one. So here is the discussion here. So here is your dark nebula, and this is the ISM. This is the space outside. When the pressure from the inside and the pressure from outside are the same, then we say that they're in equilibrium. This is how stars are actually in equilibrium too. They retain their shape because of the internal explosions. There is an outward pressure because of the thermonuclear reactions inside the core of the star, but the gravity will pull them together, so the two pressures cancel and the star retains its shape. Unless the nuclear reactions inside they are turned off, then the star collapses and explodes into a supernova. Or if somehow gravity will also loosen, like for example, when they become supergiant, then the star expands. So this is similar to that effect. So this is the pressure, has to be the same. That's how the nebula is balanced. So the pressure inside is given by PV equal to nRT or PV NKBT. So this is for the nebula. And this is the N for the nebula. KB is constant. For the ISM, the pressure of the ISM times the volume of the ISM is equal to the number of particles in the ISM times KB, which is constant, times the temperature of the ISM. Obviously, the two pressures have to be the same to become stable. Otherwise, it's going to collapse or expand, one of the two. So in this case, these two pressures cancel when I do the ratios. So the volume of the nebula divided by the volume of the ISM is equal to the number of particles in the nebula divided by the number of particles in the ISM. The constant K cancels, so you're left with the temperature of the nebula divided by the temperature of the ISM. So all you have to do is leave these two temperatures and take the ratios. So the temperature of the ISM over the temperature of the nebula, because that's how they want it. So we're going to move this to this side and the other one to this side. I will find the ratio of the density of the nebula, V of n, over the density of that of the ISM, the interstellar medium, divided by the volume of the ISM. So this is exactly what you're supposed to show. All you have to do is equate the two pressures given by PV equal to nRT, although in this pressure expressed in terms of K, so it's NKBT, and then you divide the two and you find the ratio of the two temperatures. So this is not thermal equilibrium though. The two temperatures are not the same, but the pressures are. That's what keeps the balloon from exploding or the balloon from imploding, because at some point the pressure from the air and the pressure inside, they become the same. Otherwise, if the pressure inside is more, so it's going to expand, or if the pressure from outside is higher, so it's going to collapse. That's what retains the balloon its shape. Okay, so this is similar in a sense to the balloon. Okay, so this is where this expression is coming. All you have to do is just do this expression, make sure the two pressures are the same, and that's it. And everything else should fall in part in its place. Now they take the case of the sun. They give you the ISM near the sun is 200 particles per. It's 1 hydrogen per 200 cubic centimeters. Okay, that's one thing. Estimate the temperature of the ISM in the vicinity of the sun. So we're going to do the same formula using that of the sun. So this will be the temperature of the sun. The temperature of the sun. Oh, no, you're going to find it in interstellar space first, sorry, and compare it to that of the ISM. So in Ti of this near the sun is equal to the ratio near this nebula. It's 50 times 10 to the power 6, okay, divided by that of near the nebula, which is 1 per 200 cubic centimeters. And 200 cubic centimeters is 10 to the power 6, basically, divided by 200, so it's going to be cubic meters, times the temperature, which is 20 Kelvin. Cancel the 10 to the power 6 to 10 to the power 6. 50 divided by 1 over 200 is going to be about 100,000. Is it? 1,000, 5 times. It's about 1,000 times 20. So it's going to be about.
Wait, isn't
Okay.
it 10,000?
Yeah, it's 10,000. You're right. 10,000 times 20. So that's going to be about 200,000 Kelvin. Okay. So this is the temperature of the interstellar medium everywhere. Okay. So near the sun, where the temperature on the surface is 5,800 Kelvin, immediately in its vicinity, the temperature of the interstellar space is about 100,000 Kelvin. This is a huge number. Okay, the velocity. So would a spacecraft traveling around near the sun be burned? No, because remember, you still only have one particle in 200 cubic centimeters. So it's still very little of them that they're going to encounter. Enough practice of these problems. I hope that you guys have enough ammunition to be able to solve these problems. I do them in detail, honestly, because to give you an idea how to tackle these problems and discuss them and come up with solutions to the problems that you're doing. So I think at some point, probably I ask you to finish the numbers. So that I'm expecting that you do anyway. And then that is the task of the day for today's discussion thing. And then also, even if I don't ask you, you're strongly recommended to go through the entire calculation step by step and make sure, first of all, I didn't make a mistake, because I do. And then the other thing is to understand how those things are done, because you're going to be accountable for when it comes test times. Okay.
DJ, just to clarify the further discussion, it's just 18.68 or 1868 on page 609.
You need to finish that problem. And I also asked for several other calculations that you need to finish too. Okay. So some of them, a lot of them, I did them. For this one, did I miss anything in here? I don't think I did. Okay. No, I did not include. So I need you guys to include the escape velocity in here, which is this number. Okay, for this problem, 1883. So you need to plug in the number in here because it has to be less than the 700. Because if it's not less than 700 meter per second, which is the RMS velocity, that means that this nebula is stable. And I know they are not. So this speed better be less than 700 meter per second. Okay. So I know that they evaporate over time. So this is one thing that I want you guys to make sure that we did. And of course, for your own benefit, do all of the calculations anyway. The problem 1870, I think we did it to the whole thing. So let me mark this problem because in test times.
When is the discussion post due?
It should be on February 5th, I think. Okay.
Okay.
It should be on the deadline in there. Okay. Enough talk about the lecture and the problems, applications. So let's delve into the lab now. It should be an easy lab, with the exception of that point that I was talking about in terms of the mistake, a common mistake or a common problem that I have seen time and again because of the error. I don't want you to get the error of 12% or 15% error because the errors are a lot less than that. So let me open the lab. And let me share with you the screen for the lab. Okay, when you have files like this one, it's a good idea always to open them. Don't open them on the browser. Open them on your click on the arrow down in here. And this one also for the Excel file. So I'm going to click on the Excel file first, and I'm going to open it with Excel. So when it opens with Excel, I'm going to show you how it should look like. I'm waiting for it to open. Let me stop share and let me start sharing it. So the first thing that you notice is that most likely your Excel will tell you that this could not be verified by Microsoft Defender. So please trust it, okay? Enable editing. Otherwise, you're not going to be able to add anything to it. So you have to do that. So now you're supposed to get the numbers for the temperature and the angles from the table, from the data, and plug them in here. And as you go along, the Excel will give you delta L over L naught, okay? The ratio at which the length has changed with respect to L naught. There is a formula in there, okay? It's not going to allow, if I click on this one to see it, it's not allowing. So it's a read only, but you can fill these numbers in here. So if the temperature was 10 degrees, then angle in here was 6, I don't know. So it gave me a value for delta L over L naught and so on and so forth. Notice if I finish filling all of this thing, it's going to give me an error of 12.10%. I am supposed to look at the chart. And the chart, when it's completed, it's going to give me R squared. Once I get the value of R squared, I'm going to plug it in here. This, for the sake of argument, say it's 0.995. I'm not sure, okay, if that's the one, but let's see that one. So it's telling me the error is 0.05%. That is what I'm going to report in my lab. If I don't include this part in here, after I plug in all of the numbers in here, okay, after I put all the temperatures and all the angles in here, I need to look at the chart, and it's going to give me a fit for this function, including the value of R squared. In other words, how good of a fit it is. That's what R squared is. Then I'm going to take that value of R squared and plug it in here, whatever that value might be. It could be 0.93. So be it. It could be 0.99 or 0.9, I don't know, 7, okay? So be it. Whatever that value is, you're going to write it there. So this is the mistake that I have noticed in the past that some of the students forget to do, is this last step for the R squared, to report it from the chart after they complete the entire lab. So after you complete the entire lab, you open the Excel file and you fill in the numbers in here. And as you fill in the numbers, it's going to give you two things. It's going to give you the chart, how it's going to look like, and it's going to give you a best fit, and it's going to also give you, it started doing it, by the way. I don't know if this is correct or not. The temperature, apparently, they're not supposed to be in this range at all, but it's going to give you, among other things, some value for R squared, where you're going to put it in here. Once you do that, it's going to give you your error. So now, does this make sense?
Yes, it does.
Please do not forget. Thank you very much. Okay, it's supposed to have 3 digits in here, so I think whatever precisions the Excel give you from the chart, plug it in here. Otherwise, you're going to get some nonsense errors and you're going to lose points. Okay, you're going to claim that the error is too big because you forget to do that, and you're going to lose points from the grading. So let me stop sharing that Excel file, and let me now download the PDF file. Did I download it already? I think I did. Where's my? Yep, it's in here. So let me share now the PDF file. This is where the main thing is. Delta L equal to alpha L naught delta T. This is different values for the coefficient alpha, the linear expansion for different materials, okay? And you're supposed to show that alpha and beta have this simple relationship between them. The simplest way you can do it is take a volume of cubic sides L, so L times L times L, which is the volume, and then find the to the linear value, beta is the first correction in the volume. And if you do that, then it's going to be the first term in the Taylor expansion, which is just 3 times alpha. Again, if you have difficulty with this one, please let me know, and we should be able to get this one correct, okay? So then you're supposed to do the objective. Again, we're taking an element in here, you're heating it, and you're seeing it, how well it's going to expand, and you're plotting the data, and you're going to find that this relationship holds true or not. For the linear expansion. Okay, that's all. That's it. Okay, you have delta L over L naught as your independent variable. You have delta T, which is your dependent variable. From here, the coefficient of linear expansion should be the alpha term in here that you're going to check with. So this is basically the whole lab. It's kind of easy lab, and you're going to do the lab, you're going to take the data between 0 and 10 degrees twice. 2 different numbers, okay? They should not be the same number. And 2 readings between 10 and 20 degrees, 2 readings between 20 and 30 degrees, 2 readings between 30 and 40, and 2 degrees, readings between 40 and 50 degrees. Plug in those angles in here and plug in those temperatures in here. Excel should help you with this ratio, okay? And then Excel should give you what the value of alpha is. And you have the value of R squared in here is. Alpha is going to be the slope in this case. And the value of R squared in here, which you take from the chart, in the error. And you're going to answer the questions. If it's more than 5%, what happened? And you may have to redo it. If it's less than 5%, you're in good shape. Then you're going to explain and the conclusion. So this is pretty straightforward. The only thing is, where is that animation? Okay. Let's open this. This is a GeoGebra file. So I'm going to open it and pull it by itself. Okay. And stop sharing the screen and share with you where this thing is. So right now, there is no heat involved. Okay, so you really have to be careful, okay, with this one. You have to make sure, because it's going to expand very quickly, very fast. Here is what the apparatus is. You have a rod in here. It's fixed from one end and free to move from the other. When you turn the heat on, it's going to start to expand. As it expands, it's going to push this arm, and this arm is attached to a pivot point, and this one starts to turn, basically. There is a one-to-one correspondence between the length with which this one has expanded and the angle with which it has moved. That's what Excel is giving you. It's giving you that ratio, really. Giving you how much angles did you say it moved? Then in this case, I'm going to tell you how much it's supposed to have expanded, delta L over L naught. This is L naught, and delta L is the amount that has increased. So if I turn on, this is delta T, by the way, that is going to be recorded for you. Okay, so it's not T. So I'm going to click on turning this thing in here. I moved it. So right now 6, 7, 8, 9 degrees. So and read the degrees and the temperature. It's going to be fast, so you have to really be careful in here. You might to do this one several times. You might to turn it off, and if you turn it off, you will wait for it to cool down. That's what you do in the lab, actually. We turn it off, you have to really wait for it to go back to its original length. Okay, and you can catch the numbers in the backward too while it's cooling, and record these numbers in there. It's going to be, so you have to really be fast in here to get your numbers to minimize that error. Or another way of doing this, are you looking at the GeoGebra file or not, everybody? The GeoGebra website?
Yeah.
Okay, very good. So again, it dropped back to 0. So now I'm going to turn on the heat again, basically this thing in here. And oops, I don't mean to do this. So if you're proficient with GeoGebra, you can play with this thing in here, okay? And so on and so forth. Okay?
Is there a pause option on the simulation?
There is no pause option in simulation. Okay? Because heat, the problem with it, even in real life, is it's a power. Okay? So the minute you turn it on, it's coming at that rate all the time per second. So if you're doing this apparatus in the lab, and if you don't have any digital equipment to capture those readings for the temperature and the length in this case, and if you don't have, like I said, those digits, you really have to do it with hand. This is an outdated apparatus. This is how it was in the old days. Okay, in the early 1900s, this is what people did. They didn't have digital equipment to get them the readings. So this is simulation of that environment. I think, I'm not sure if in the lab we have this one, at least in another campus. That's how I simulated this thing using somebody else's campus apparatus, because they have this outdated equipment. So that's what I tried to do, simulate it, even with the errors in it. Does this lab make sense to you guys?
It does.
Yeah.
Should be straightforward. The only thing is, the only catch problem that you might encounter is that R squared, if you forget to include it, and you end up with an error of 12%, that doesn't make sense, okay? So go back and fix it and try to do it as careful as you can. Once you do it, you're going to get your data, and you should be able to get that delta L over L, not
How
as a
are we
function
supposed
of
to get the R squared?
from the Excel file. Again, let me, because this is a very important step of the process. Once you plug in the numbers in here, okay? I don't know, I'm just putting the angles in here, okay? Delta T, let's say, for example, it's 12 degrees. So delta in here, let's say if it was 4, and let's say now it's 7, okay? And so on and so forth, okay? So this is the numbers that I have in here. So let's just, for the case, for the sake of argument, let's make it 13, and let's make this one 8, and let's make this one now 1 to 19. And no, this one 8 is no good. So let's make it 10 or 11. And let's make this one 18. Okay, I'm not sure. Okay, I'm just plugging in numbers in here, and you can clearly see that the value of alpha now is giving me this number in here from the Excel file. If I look at the chart, it gave me, first of all, a fit function which is the dotted line in here, trying to make it as line as possible. Okay. And it gave me an R value of 0.966. Who asked it? Was it Helen who asked the question or somebody else?
It was me.
Okay, so now you have R squared, not R. Don't square root this thing, just leave it the way it is. So it's 0.966. So I come in here and delete this number, whatever it was, and write it 0.966. Okay, and the error now is 3.4%.
Okay, the chart is also on the Excel file.
I'm sorry, the chart is on Excel file. Yes, both of them, the data and chart. They're in the bottom. If you look at the, do you see it in the here or not? Do you guys see my screen?
Yeah, we can.
Yeah.
Yeah. So just switch between the chart and the data.
Okay,
Okay, so the chart will give you R squared. So that's where you put it in, and that's how you get your error. And that's how you get your alpha also as you're going through this data. Don't use these numbers. These numbers are just some nonsense thing that I just put in there just to see that it works, okay? Just to give you a rough thing in there. Okay, so these are just numbers that I throw in there just to see if it fits a line or not. But it's supposed to be a linear thing. Make sense for everybody?
yes, it does.
Yeah, makes sense.
Yep.
Okay, very good. So it's a very simple lab. And the simulation, I gave you the link for it, the instructions, the Excel file, and everything for you. So I guess, do you guys have any questions for me before I end the recording? And stay in here. I'm going to stay in here. And if you guys want to work on the lab now, it's fine. If not, you can leave and basically do it on your own time later on. Do you have any questions first for the lecture and the lab? Because we're done with chapter 18 too.
Can you like repeat the problems one more time for the discussion?
Problem 1868, you're supposed to do the numbers, okay? And that question from 1883, you're supposed to find the escape velocity in the nebula and compare it to the RMS velocity. It should be less. It should be less, meaning that the nebula, there's too much heat in it of 20 Kelvin, even though it's 20 Kelvin, it's high enough temperature that the hydrogen atoms will escape and it will lose its material over time. So it's going to shrink in size until it evaporates. If the number for the escape velocity is less than the RMS velocity, the RMS was 701 meters per second, and the escape velocity, according to what I know about nebulae in general, is for a hydrogen atom nebulae, is that they are volatile. They are supposed to evaporate over time, okay? So you're supposed to find the speed, escape velocity less than the RMS speed.
Thank you.
Got it? No problem. Any other question?
No.
Okay, so I'm going to stop the recording and I'm going to hang around till the last person leaves, and I'm going to stop it. And I will see you guys Tuesday.
Thank you, DJ. We'll see you.
See you guys.